Here's the solution to the quiz. So reminder, we had two transfer functions, actually the same transfer function g of s, one part in open loop and the other part in closed loop. So we need to write the transfer functions h1 and h2 and then determine stability. So remembering that g of s is equal to 1 over s times s plus 1, we can start by writing the transfer function h1 of s. So that's actually just equal to 1 over s times s plus 1. If we decide to write out the characteristic equation, multiplying it out, delta of s is s squared plus s plus 0. So we're missing the 0s, s to the 0 term. And so if any of our coefficients are equal to 0, this fails the necessary condition for stability by Routh-Hurwitz. So therefore it's unstable. You could also just plot the poles and say, well, we have a 0 at s equals 0, therefore our system is unstable because one of the poles is on the j omega axis. Okay, so here we have h2 of s. So whenever we have a feedback loop, this is how the transfer function looks. So go back and review one of the previous lectures where we derived this if you're confused on this. So the transfer function h2 is g over 1 plus g. So if we go ahead and add the transfer function 1 over s times s plus 1 for g, and then we multiply top and bottom by s times s plus 1, then we see that we get something that looks like this. So 1 over s squared plus s plus 1. So we're able with feedback to add an extra term to our characteristic equation. So now we're no longer going to have a 0 there. So we'll be able to now evaluate the stability of the system. So is it stable? Let's go ahead and write the characteristic equation. So we have all of our terms greater than 0. So now we can use Routh-Hurwitz. So I'll go ahead and construct the Routh array over here. So we begin with 1 for the s squared term, and then 1 for s to the 0. Moving to the s1 row, we use s to the 1, and then we don't need a value for s to the 0, or if you really like, you can go ahead and add a 0 here. So now we need to calculate b1, which is our s0 term. So we calculate b1 as 1 times 1 minus 1 times 0 over 1. That's just going to give us a value of 1. So if we now look at the left-hand column, they're all positive. So we have no sign changes. Therefore, the system is stable because there are no poles in the right-hand plane. So that's the solution to the quiz. One important thing here is that all we had to do was add feedback to this system, and we stabilized it. So later we'll have to do more complicated things to stabilize a system. But for this particular system, all we had to do was add feedback, and we got stability for free.